All right, thank you. Yep, I see it is being recorded. Okay. So I'll go ahead and get started. It looks like we are at 1 o'clock. And I imagine people will still be joining, but most of my remarks are more just generally introductory. Can folks see my slides okay?
Yeah.
Okay, great. So this session focuses on the work being done by the applications integration part of the project. So it's a pretty large number of people doing a lot of work to make the applications and SD projects functional on all three of the facilities: Machines, Frontier, Aurora, and Perlmutter. My name is Scott Parker. I am the L3 for this area, along with Balint Ju. And I was planning on just giving a short intro. I know we probably have people outside of AppInt who are joining. For AppInt folks, this will all be very familiar material, but just to kind of give people a frame of reference for what we're doing, what our role is, and what they can expect from AppInt folks and expect to hear about later in the session. So the applications integration portion of the project funds staff at the facilities and vendors to work with the AD and SD teams, really to enable their codes to run on the respective platforms. And these are meant to be sort of persistent long-term engagements. So the idea is that the AppInt staff would be really part of the AD and SD projects to a large degree. And this kind of brings together the people that have knowledge of the code with the AppInt folks that have knowledge of the hardware and the system software environment, and help them resolve issues. And so we manage these engagements through what we call technical execution plans. So these are just written documents that lay out sort of plans for future work. They're very dynamic. They're not carved in stone, but they're meant to sort of outline a plan, or at least a common agreement on what work and what priorities there are. And in many cases, the AppInt folks have worked with these teams for a long time in the past. If they're new, they may not have had that past relationship. But I think during the course of this work over the years that we've been doing this, most of these folks have become very embedded in the team and very involved in the discussions that they have. I think the advantages that we see AppInt folks from the facilities bringing to the projects are the information that they have about the vendor systems and the hardware and software. Typically on the facility side, we're able to get the latest and greatest information and make sure that gets shared out to the project folks, and particularly the information that they really need to know, because often there's a lot of information and it's hard to keep up with everything. We also often jump on the early hardware as sort of the first wave of people that get on, and that's both a blessing and a curse. Usually there's a lot of issues there, and we try to shield folks from that, so we get on and try to find as many of the broken things as we can and get them fixed before bringing the broader community on, and in doing so, spare them some of the pain of getting on these early systems. And another facet to the applications integration work, beyond just the work that's being done by the facility staff, is also the work being done by the vendors through the LCF Centers of Excellence. And so these COEs are basically funding for staff at the vendors to work in a committed fashion with our applications folks and the projects to resolve issues. And there we get expertise directly from the vendors, who have obviously in most cases the most detailed knowledge of the hardware and software, since they built it and wrote it. And they also provide workshops and hackathons and training and such. This slide just kind of gives an overview of some of the activities we're commonly involved in. I won't read through this in length, but a lot of the work we do goes into porting and debugging and optimizing applications. We also serve as a conduit between the facilities, the vendor center of excellence, and the projects. So we kind of stay in the loop, and often the vendors people speak a slightly different dialect of HPC than the software developers on the AD or SD projects, and sometimes we're able to help smooth that and translate. And we also make sure that like I said, there's a lot of information out there, that the appropriate information is routed to the teams, that they're on the appropriate NDAs, that they're in the loop about training events, system upgrades, and so on. This table shows the engagements that we have with the AD projects across the three facilities, and you'll note that no facility is working with all of the AD projects. We unfortunately just don't have the money And even if we had the money, we probably couldn't find the staff to do that very easily, because it's really hard to find people who are good at this, good in this role. And so, there's a distribution of engagements across the facilities. However, every project is engaged with at least one facility, and in many cases they're working with two, or in a few cases three facilities. And we're also working with the SD projects. There's a lot of SD projects, and the initial plan didn't provide quite as much funding for engagement with ST, so it's a little, I guess, a little less coverage in the ST space. But I think between the three facilities and the work that the vendors are sort of doing independent of the applications integration work, we have good engagement with the ST projects. And when I say work independent of App-In, in many cases, the vendors have sort of long-standing relationships with some of these SD projects, and so they're getting help through those mechanisms that aren't directly funded by App-In. But the kind of work is very analogous. I did want to introduce the three L4s at the facility for the applications integration work. And, at the facility, this is really where all the work is being done. And it's really, Chris, Stephen, and Debbie that have been doing all the work and leading this effort, hiring the folks, getting them oriented on projects, making sure all our milestones and reports are completed on time, and they've been doing an excellent job with that. And they'll be talking a little bit about the work that they've been doing and an update on their facility. And I also wanted to just briefly show, all the folks that we have on App-In. This slide is from a couple months ago, so it's possible that there may have been one or two people that have come and left that aren't captured here. But I did want to thank all of the App-In staff across all the facilities. Folks are doing, I think, outstanding work. And I think their contributions to ECP, have been really significant in terms of, enabling the applications and ST projects to make progress, as much as they have been on the systems. And I will mention also, again, like I said, it's not just the facility staff, it's also the COEs. So this is just some of the folks that we work with on the vendor side. AMD and Intel have slightly different models. Intel has sort of fully dedicated staff, so we get 100% more or less of these 6 people listed here, whereas AMD has a wider range of people that we get a smaller chunk of their time from. And I'll just throw up real quickly a few comments from the IPR that was held recently. So this is the annual review of ECP. And there were a number of positive comments about the application integration work. That one comment was that, these activities are critical to the science success at the beginning of system production. And that, expanding this would be an excellent expenditure of remaining contingency. And so on. So I think the reviewers were very positive about the work that we've done. And I want to thank everybody who is working as part of application integration for making that the case. And with that, I will stop talking. This is the agenda that we have. So the next folks up are the L4s, Debbie, Stephen, and Chris, who will be talking, respectively, for a few minutes about the work at their facilities. And then we'll turn it over to the App-In folks themselves to talk about a few, and this is really just a subset of the projects. And one thing, when we've done these meetings in person, this has been sort of an opportunity for App-In folks to talk to each other and interact with each other. Unfortunately, we kind of lose that in the virtual environment. And so, to at least do some approximation of replicating that, we asked the App-In folks at the 3 facilities to work jointly and put these presentations together. So there'll be a mix of people from the 3 different facilities involved in these talks, and hopefully that at least replicated a little bit of the interaction that we've gotten in the past for an in-person meeting, and hopefully next year we'll be able to do this in person. And so with that, I will stop sharing and I will turn it over to I guess, Debbie, do you want to go first?
Sure, I can go first. I'll go very quickly through my slides. I don't want to take up too much time in the agenda here. After Scott's introduction, I don't think there's a lot additional that I need to add for what we're doing at NERSC. So the main sort of news from NERSC in terms of system deployment is around Perlmutter. And if you saw the talk this morning from Sudeep about work going on at the facilities, in the facility session, you'll have already got a lot of this information. So the phase 1 of Perlmutter with the full complement of GPU nodes has been operational for some time now, around 6 months. It's been very productive. We've had a large range of science projects, including all the ECP teams running on Perlmutter. We have something like 216 science projects who've been using the GPU node in Perlmutter so far. The phase 2 part of Perlmutter is the CPU only nodes. This is the AMD CPUs. They are being delivered and installed right now. In fact, we're in the process of doing starting the system integration now. And so any of you who are NERSC users will be hearing updates about that through our weekly emails as we go through the integration process. And we're trying to do that with as minimal impact as possible on our users who should be able to keep using their GPU partitions. All right, so this is our full set of NESAP teams. And I just want to make the point here, NESAP is our application readiness program. And we support a large set of NESAP teams who have had early access to Perlmutter. The teams here highlighted in gray are the teams that are explicitly supported by the ECP application integration effort, so directly through the AppInt funding stream. You can see that we have the teams in the gray boxes here. In addition, all the teams that are highlighted in red are ECP teams. So you'll see that we have a number of ECP teams who are part of NESAP, but that are not explicitly supported via the ECP AppInt area. And so that's just a point I want to make. The work that NERSC staff is doing supporting ECP projects goes beyond the AppInt, although that's what we're going to be focusing on in today's session. So these are our people. This is our AppInt team. Give a lot of credit to these 10 staff and postdocs who've been doing fantastic work in the last few years. We'll be hearing from some of them later today. And the one thing that I want to highlight is that we also have a dedicated ST team at NERSC. There's some overlap in some of the names here. Some of the people are in supporting AD teams as well as ST teams. But this is something that we have really started up in a formal way in the last year. So some of you on this call may not have heard about the work we're doing here. And so I just want to give a very quick overview of the areas in which we're supporting the ST teams at NERSC. This is in 3 different areas: in math libraries, focusing on HDF5 and IO, and also in Cocos. So in math libraries, we've been working with the SuperLU team on Perlmutter, as well as profiling and optimizing Alexa ArborX on Perlmutter, and also working very closely with the XGC team, evaluating and integrating the Ginkgo solver in there. For HDF5 and IO, the team has formed and kicked off a task force looking at IO performance. This is something we're very excited about. And thanks to everyone who has been involved in that and has responded to requests for participation in this. There's an IO benchmark suite being developed based on the ECP HDF5 application. This is H5 Bench, and includes benchmarks for a whole variety of different ECP apps, which is making really good progress. We're also working with Cocos, extending the scope and impact of Cocos, making improvements to the OpenMP target backend, and also working on PyCocos via exa-mini-MD. So you'll hear about this work as well in other sessions in the ECP annual meeting, and particularly in the OpenMP and the Cocos sessions. All right, so that was all I wanted to bring up for NERSC.
All right. Yeah,
Thanks,
thank
everyone.
you, let's see, Stephen, if you're ready, would you like to go next?
Let me jump in here and start everything up going. That should be it. Can everybody see my screen?
Yep, that looks good.
Alrighty. Well, I'm Stephen Nichols, and I'm a computational scientist at Oak Laboratory, and I'm just going to kind of give a very brief overview of what's happening at LCF with Frontier AppInt. And one question that comes up very frequently is, when will ECP teams have access to Frontier? And the quick answer is, we don't really have a specific date circled on the calendar yet, but we are targeting the month of July, and a lot of people are working really hard to keep the machine ready to go and to make it available in this timeline, and to really make this a realizable date. So I am asking for your continued patience for just a little bit longer because we are almost there. We currently support and work with 14 applications, the original 12 in the top block. And we added some help for Candle and exa-scale over the past few months, largely because somebody asked a question. And so if you're a project out there and you think you would like to have some additional engagement with Crusher and Frontier, please send an email to Belinda and me to start that conversation. We can't make any blanket guarantees on the level of engagement that we can provide, but we would like the opportunity to help. So the bottom line here is to send that email and start the conversation. I'd also like to remind everybody of Crusher office hours. We're starting that this month. It is open to all Crusher users, and it'll be a time to meet with HP, AMD, and ORNL staff members to talk about a variety of problems. The one caveat here is that you have to sign up at least 1 week in advance. So it is too late to sign up for May 9th session. And I bring this up largely because I want to make sure everybody's getting the emails. All Crusher users should have received an email about a week and a half, 2 weeks ago with sign up information. If you are a Crusher user and did not receive that email, please let me know. I can forward that information and we can get that corrected for next time around. We held 2 Crusher hackathons back in February, and they were very successful, so much so that all the teams asked for more. So to meet that request, we are planning 2 more Crusher hackathons, one in June as a purely virtual event, and one in August with a potential in-person component as life slowly returns to normal. These will have the same 3-day format as the February session, and any kind of question with this can be directed to Tom Papa Theodore. And finally, I'm going to close with a couple reminders here. The first is to submit all Crusher results to help@olcf.ornl.gov before you present them publicly at a conference or submit them to a journal. And finally, and maybe more importantly at this point, is that you have problems on Crusher and even going into Frontier, please don't be that user who is waiting simply for a mature software stack. Let me remind you that these tickets are a very strong component in how we build a mature software stack. So please submit those tickets. Thank you.
All right, thanks, Stephen. And let's see, I'll turn it over to Chris next then.
Here we go. Slides coming across.
Yep.
Great. So I'll be quick. I don't want to repeat a lot of what Scott, Devin, and others have said. Sorry. So here with the APID team at Argonne, we're engaged with many of the AD projects. And so I just showed the list here is if there's anybody else from the APID team at the other facilities or someone on one of the AD teams and you're ever looking for help, we have this list. I maintain it on the DCP Confluence page, and so that there's always a name to the projects that we can offer assistance with. And we're growing. We're looking for additional effort, both in terms of a couple of the contractors that we have working with us on a couple of the projects, and in open postdocs positions that we're in the process of filling. So there's a lot of activity going on as we get ready and help teams prepare for Aurora. I'll show a bunch of names on the next slide as well. And Scott had already shown this in his. And so these are the dedicated Intel folks that we work with. So across the board, many on the APID teams and the AD and the SD projects teams work, in many cases directly with the Intel folks. And so I list again all the projects here just as one way that folks can connect. I think another way that all of us could connect better, across the APID facilities and outside is if we're working on commonalities, whether similar programming models, similar libraries, interfaces to those libraries. A lot of us are dealing with performance portability aspects and how we tackle that across multiple GPU vendors. And so I think there's a lot of opportunities to use these names to project mappings that all of us have shown that, to develop and spur other collaborations. And so if you ever have a question of how to port, say, OpenMP to SYCL or vice versa, or how this particular algorithm ran on this particular hardware, what does it look like in other hardware? There's a lot of opportunity here with all the great work that we and APID are doing. And so if anyone here is looking to connect and they're not sure where to start, please, you can reach out to me for any of the App and Intel COE staff, but additionally, Mike DeMello is a very good resource to connect with folks. So the vast majority of the work that App folks have been doing over the years has been primarily enabling teams on the Aurora testbeds. Folks familiar with this have known that we've been working a long time with the Iris integrated GPUs, more recently the discrete GPUs. For folks that have been attending many of the Aurora sessions, you'll be aware that we now have PVC nodes in JLSE, and then we're slowly opening up access to the broader ECD community. And so really that's where a lot of the effort is focused on engaging with teams across the board. And so if anyone is here that's interested in getting access to the testbed and doesn't already have it, there's information on the ECP Confluence page. If you look for Aurora Early Access, Arcticus Florentia, you should quickly find a page, and then next steps to start getting access. One of the biggest measures of the great work that everyone is doing, and again, with the current situation in NDAs, we're not really able to say a lot in a public setting, but if you saw Scott's plenary session this morning, you might have saw these slides. So this by far is one of the best metrics of the great work that everyone has been doing. We still have some work to do, but there's a lot of favorable progress on the Arcticus platform, and we're very quickly pivoting towards having a similar great progress on PVC, as Aurora is very closely approaching around the corner. And so to finalize, App staff, in addition to engaging with the teams, really working closely with them to debug issues. Initially, we were focused on functionality. We've now pivoted to performance, and we're going to pivot again to full node architecture utilization. Involved in multiple training events. For those who have access to the JLSC testbed, we will be doing a hands-on session tomorrow where many of the App team members will be participating and helping out. And in addition to the upcoming workshop. And a plug again is I think all of the facilities are about opening up and communicating and collaborating with everyone, the broader ECP community. And in Argonne, we're with PVC now in JLSE and the associated NDAs around that, we're in a position where we can now open up our biweekly applications working group meetings to the broader ECP community. And so for those who are interested and want to discuss issues and talk about your progress and anything that you're facing, please reach out to me directly if you want now, or stay tuned for an invite soon that'll be coming to that mailing list. And again, that's for folks who have access. And so multiple reasons to request access to the JLSC test, but if you don't have it already. And with that, that's it. Thank you.
All right, thanks, Chris. So that kind of covers the updates from the facility side. So now we want to kind of turn and take a look at the applications themselves. And I believe the first one we were going to hear from is the Candle project. There are 3 folks involved in putting together the presentation today: Venkat Vishwanath, Murali Amani, and John Gonley. And I'm not sure who from that group of people is going to start talking, but it looks like we got some slides up, so I'll let you go ahead.
Okay, thanks, Scott. My name is John Gownley. I'm a computational scientist at Oak Ridge, and I'm going to be talking about the part of Candle and what we've been doing on Crusher. So particularly for Oak Ridge, we're interested in the Candle's collaboration with the DOE NCI partnership in a project called Mosaic. And Mosaic is doing deep learning models mostly for natural language processing, looking at clinical text and other sorts of biomedically related text data. From a software perspective, we're basically all in PyTorch or TensorFlow, and then relying on a lot of frameworks like Hugging Face transformers, some of the big transformers libraries like DeepSpeed and Megatron, and then looking specifically at the AMD ecosystem, MIOpen, and then RICL. In terms of where those things are on Crusher right now, we're at the point that PyTorch and TensorFlow are pretty easy to install, particularly PyTorch on the system. Everything works. We're pretty happy there. Some stuff like DeepSpeed has really been fully ported over to AMD. Other things like Megatron, we've sort of got a HIPAA procedure that we can do, and they're not quite running natively, but they're pretty much there. So thinking about some performance for some of our apps, on the left-hand side, we have an app that's very closely related to the Candle challenge problem. And in this one, we're really just interested in single device performance. So we've been running this in TensorFlow just because that's sort of what we'd originally done the development for several years ago. With sort of the changes in the ecosystem, and then with much stronger AMD support for PyTorch, we've been kind of switching over to a PyTorch model these last couple of months. And we're at the point now that running on one GCD on the MI250X, we are seeing meaningfully better difference than we are on the V100 from Summit. Some of the other work we have going on is looking at larger models, particularly things like transformers. So we've been comparing some of those on a node level basis here, looking at Summit and Perlmutter as a comparison for a Crusher node. So we're very happy at this point where we are seeing performance on a Crusher node, meaningfully exceeding that of what we see on Perlmutter. And as you can see from my very simplistic roofline plot there, there's a little more room that we expect to improve. Beyond that, current work is really focused on scaling right now, and then starting to look at larger models and then some different models that include sparse attention as well. And this work is mostly with Isaac Lingus at OLCF, and then Mengshu Wu at HP has been very helpful as well.
Good. Thanks, John. I'm Venkat Vishwanath, and I'll cover some of the work that's ongoing with the Candle ECP project at ALCF as part of the application integration. This work is primarily being done at the ALCF side by Murli Imani, so all kudos to and efforts are his. Murli is actually joining us remotely as well while he's on vacation, so thanks, Murli. So as part of the Candle ECP project, there are two key workloads that they have today. One is the drug response problem UNO, and the second is the P3B4 that John earlier mentioned about. So both these models are fully functional and they work on the Intel GPUs. One key component of the Candle workflow is that they are really looking at least if you're looking at the drug response, very high throughput screening, in this case their models are, at least the UNO model is in the couple of million parameters, and you can fit several of these on a single GPU. So as they're trying to really screen through millions of these I would say through millions of compounds or drugs that they want to do a screening run, they are interested in a very high throughput regime, and we are now able to run multiple such instances on a GPU effectively. So this is also now fully supported on the Intel GPU. So these are components that will really help with some of the challenge problems and the figure of merit that's needed. Our current focus as part of our efforts is to really improve a lot of performance that we see. And we have very promising results in this direction. I'm sure once we're more openly able to talk about this in other forums, we are happy to go into details here. We're also looking at various precisions as part of this effort. We are very excited with the results that we are seeing here. The current efforts that we are focusing on is as part of the challenge problems that the ECP application team is focusing on is to look at large language models here. And in this case, they're trying to use this to generate candidates that they can then apply some of the response models, such as UNO. Our effort today is to work to enable these to run on the Intel GPUs, and these are models that also need to be scaled out. So these are efforts that are all ongoing as part of the application integration effort. In terms of just the software stack, what we work today are with deep learning frameworks such as TensorFlow, PyTorch, that cover these models on the Intel GPUs. So with that, we can happy to take any questions. John, Murli, and I are here. We can either take questions now or happy to even do it at the end.
Yeah, if there are any questions for Venkat or for John, please feel free to ask them. And if not now, we should have some time at the end of the session if people, if questions occur to people later on. If not, thank you, John and Venkat. We'll go on to the next presentation covering the Excel project. So that's Rahul, Gayatri, Neil Mehta, Yasemin Gadar. And so it looks like we've got some slides there. So why don't I see them? So go ahead and
okay, does the slide look good?
Yep.
All right. So hi everyone, my name is Yasemin Gadar and I am a computational scientist at Argonne Leadership Computing Facility. And I'll be talking a little bit about Exals and Rahul will be taking over after me. So Exal is basically one of the ECP projects that is using molecular dynamics simulation, specifically LAMS package, as their main compute engine. So the potential that they are interested is called a SNAP, a spectral number analysis potential. And as just a note, LAMS is a program written in C, C++. For the prioritization, it uses MPI, OpenMP, and is also GPU enabled using COCOS, CUDA, and so on. The performance directly depends on the single node and single GPU performance of a SNAP, and that's the main focus. So the status of Aurora, so up until October 2021, the focus was on Test SNAP, which was a mini app representing the bottlenecks of the SNAP LAMS package. But at that point, we were able to actually put the full application on Aurora, and today LAMS as a full application does compile and run correctly on Intel's recent hardware and software. And we are basically working on investigating the performance of the Exalt workload in LAMS on Intel GPUs, and also have been doing some scaling studies as well. There are multiple COCOS backends for the LAMS SNAP that it basically uses a different, and it's being pushed constantly and being developed constantly today. I am not showing any results on the current hardware, but it does run and compile correctly. And then the other thing is there's two main backends that currently we are focusing on. One is OpenMP Target, and the other one is SYCL. SYCL runs correctly and compiles correctly. The OpenMP backend does have some issues that we are working on to resolve. And again, all the updates are being directly pushed to the public LAMS repo. Rahul is going to taking over and discuss further details about the status of Exalt on the NVIDIA and AMD GPUs.
Hi, thanks, Yassi. Can everybody hear me?
Yeah.
Okay. Hi, so I'll be talking about the status of the project on NVIDIA and AMD GPUs. As you can see on the left side, the figure, it gives like a bird's eye view of where the project is with respect to different GPUs available to us, like the NVIDIA's A100 and V100 GPU, and the AMD's MI100 and MI250X. The x-axis shows the progress of the project over time, and the y-axis is essentially a metric of throughput. So the higher the number, the better the throughput. So that's what we're looking at. And as you can see, every update that we have done to the SNAP implementation has improved performance on almost every GPU that's shown here. of course, there is the NVIDIA's A100 GPU is leading in terms of its benefits, because for a long time we were focused on improving the NVIDIA GPU's performance because that's what was available to us. And recently we have started focusing on the AMD GPU performances. Currently, we see nearly a 2.4x difference in performance between AMD's MI100 versus NVIDIA's V100, and a comparable difference between NVIDIA's A100 and MI250X from AMD. We are currently trying to resolve the issues that are arising because of which such a performance gap is arising. Some of the issues that we boiled down to for the reasons being for this performance differences, smaller L1 caches on AMD GPUs, and that is impacting our performance of Snap tremendously. For example, on NVIDIA's V100 GPU, we hit the L1 cache more than 90% of the time, whereas on MI100, that drops to around 62 to 63% of the time, the L1 cache being hit. And one of the reasons was the smaller L1 cache. The other thing that we noticed was the HIP compiler was unable to generate optimized FMA instructions when the COCOS framework was used as the front end. So essentially, this was also observed when we were running a simple COCOS stream and flop benchmark, right? And we are trying to resolve that issue in conjunction with the AMD developers. Next slide, please. So while that was like till now we were talking about the actual exalt figure of merit problem, the SNAP one, but we are also focused on other potentials in LAMP's package. Like we're constantly testing Lennard-Jones, Tursoff, and Snap on NVIDIA AMD and MI100, sorry, NVIDIA AMD and Intel architectures, and we are testing them with all the GPU ports of LAMP's potentials are using COCOS. So essentially, for NVIDIA GPUs, we use the native backend with CUDA, for AMD HIP, and for Intel SYCL. Apart from that, we're also trying to develop the OpenMP target backend and see how efficiently can we run the LAMP's potentials with the OpenMP target backend on the respective GPUs. So for that, we use LLVM 13 on NVIDIA. Until now, we were using LLVM 13 that comes with the ROCm compiler stack. And on Intel, we were using ICPX. Next slide, please. So this is a performance comparison of Lennard-Jones on NVIDIA's A100 and AMD's MI100. The blue bar is showing the performance of the native backends on NVIDIA with CUDA and AMD's HIP, compared to the red bars show the performance of the OpenMP target backend of COCOS. And as you can see, there is a significant performance difference between the two backends, and we are trying to work on that. Next slide, please. In this, we are actually showing a similar comparison for the Tursoff potential, and the difference between the Lennard-Jones and Tursoff is that the relative difference between the backends on NVIDIA is higher compared to the AMD backends. And we are not sure why we are observing this difference yet, and we are working towards it. There is no advanced COCOS constructs being used here. Like we are using simple constructs such as parallel for, parallel reduce, some hierarchical parallelism, and custom reduction. Nothing fancy, but still we observe this. Okay, next slide. This is Test Snap, which is a proxy app for LAMP's Snap potential, as which Yassi was mentioning earlier. There are two versions of Test Snap. One uses scratch memory, which is essentially using shared memory on NVIDIA GPUs and AMD GPUs to store some intermediate results, and one that does not use scratch memory and uses global memory instead to store some intermediate results. The issue with using scratch memory with the OpenMP target backend is that there is no way to explicitly ask for shared memory using OpenMP constructs, at least not efficiently yet. And so what the COCO's backend, OpenMP target backend does is it instead stores this, whatever scratch memory was requested in the global memory, which means it has a negative advantage compared to the native backends because it does not take advantage of the low latency local storage memory that's available on GPUs. And that's why if you see the performance comparison between the scratch versions in the native and OpenMP, the blue and the red bars, you see the relative difference in performance is quite high. But if you see the non-scratch versions, the yellow and the green bar, the relative difference is pretty low between the two backends. Next one. This is the performance that we have observed but when running the actual LAMP snap potential with the OpenMP target backend on NVIDIA's A100 GPU. Until now, we were only able to run the snap potential from the actual LAMPS package only on NVIDIA GPUs. And we have observed that there is a relatively high performance difference between the native backend and the OpenMP target backend. In this case, we are using the scratch version of the algorithm that we were discussing in the earlier slide. We were not able to run the non-scratch version because in the LAMPS, in the actual LAMPS repo implementation, the scratch version and running on and the GPU version are tightly coupled, and we cannot separate the usage of scratch implementation with the device from the device versions. And that's why we're not able to run the non-scratch version. Along the way, we realized a few things that we could not, like when the code gets too complicated, we were unable to capture the this pointer in the target regions. And so we had to do like a workaround that you can see in the right side on the bullet point 2, where we create local copies. And we realized that we were also getting wrong results if there were less than 32 threads per team on NVIDIA GPUs. On AMD GPUs, we are not yet gotten correct results. We were able to compile, but we're getting wrong results. The snap implementation in LAMPS uses slightly more advanced COCO's constructs such as scratch memory and team scan. So the fact that we were able to run this with the OpenMP target backend was, at least we consider it a success in the current stage. We're working towards getting it more efficient and to get it to run on more than NVIDIA GPUs. Next slide, please. So in conclusion, we want to say that the Exalt FOM, at least, can be run on all the 3 GPUs, NVIDIA, AMD, and Intel, with the native backends. And because it is using COCOs, it's a portable solution with no change to the code. Right? And the other potentials that we were considering, like 2 out of the 3 potentials that we are considering, can run with the OpenMP target backend on all the 3 GPUs. The snap potential can run on NVIDIA GPUs with the OpenMP target backend. Next slide, please. This is just our plan on what we are doing, what we are actually considering to work on in the future. On AMD GPUs, we want to build successfully the OpenMP target backend and try to work on improving the performance of the snap potential on AMD GPUs with the COCO's HIP, that is a native backend of AMD GPUs. On NVIDIA GPUs, we want to work on fixing the performance regressions that we see in the OpenMP target backend of COCO's. And on the Intel GPUs, we want to resolve the issues with the OpenMP target backend and and improve the LAMP snap performance with the COCO's sickle. That's it. If somebody has any questions, I can. And we definitely want to acknowledge everybody else who's been helping us, Patrick and Daniel Arndt from COCO's team, Chris Knight, and the Exalt team. If anybody has any questions, I'd be.
Yeah, are there any questions for the Exalt folks, for Yassi or for Rahul? All right, well, thanks, Marco, thanks, Yasi. And so now we'll move on to the final application presentation from E3SM. And so that will be from Matt Norman and Abhishek Bagusetti with help from Hannah Ross. All right, I see the slides. Not hearing anybody.
So here we go.
Okay, there you go. I hear you now.
So yeah, I'm going to talk briefly about the E3SM MMF application integration efforts with a lot of help from Abhishek. So I'd like to acknowledge resources from Oak Ridge, ECP, and Argonne. So the E3SM is a high-resolution climate model developed and funded by DOE to resolve three main science targets: the water cycle, the cryosphere, and biogeochemistry cycles. It is a coupling of five main components, though there are more. And those components, roughly in terms of expense, the atmosphere is the most expensive. Then we have the ocean, land surface model, land ice, and sea ice. In our current high resolution kind of traditional simulations, we're running at about 28-kilometer average grid spacing in the horizontal. One of the things about climate, the uncertainty for future climate projections is very strongly influenced by clouds, by moist convection, but we only begin to resolve that at around 4 kilometers. Preferably, we'd like something around 1 kilometer or less if we could, have our way. But that would, in a global simulation, would require about 22,000 times more computation if you scale the time step with the grid refinement. One of the challenges of climate that's unique, not very common in the other applications, is we have to run at 5 simulated years per wall clock day. That's about 2,000 times real time. And to achieve that kind of throughput, we have to strong scale pretty significantly. And what happens is we have very little workload per node. And I can talk about this offline if you want, but if we consider grid refinement and strong scaling, because of that throughput requirement, there's only so far we can strong scale while keeping the simulation running at 2,000 times real time. So we can't just refine our way all the way down to cloud resolving scales if we want to keep running hundreds of years of climate under multiple scenarios like we need to. So we need some kind of algorithmic advancement to improve cloud resolution while also not requiring this kind of massive amount of computation and scale up that we probably cannot achieve in a traditional PDE's discretization. So the multi-scale modeling framework is the target that we have chosen for the ECP project. And what this is we embed a high resolution cloud resolving model at every grid model in the global model. So you can see a schematic over here on the bottom right, where there's this hurricane over here, and we don't really know what's going on with the clouds inside this 28 by 28 kilometer cell. So to get a better idea of that, we explicitly simulate clouds in that cell, but over a reduced domain. Oftentimes that means 2 dimensions instead of 3. So you can think of this as a middle ground between these less accurate heuristic parameterizations for deep convection and full explicit cloud resolution. We do have another project called Scream that is doing brute force cloud resolution at about 3 kilometer grid spacing over the entire globe, but clearly they can't run at 2,000 times real time, so their time scales are significantly reduced, probably to the scale of years, maybe a decade. Another interesting fact is when we do the multi-scale modeling framework, when we have a cloud resolving model and adjacent grid points, they do not directly talk to one another. So that means that the vast majority of the computation in the model no longer has MPI communication interrupting the computations. So this was a really good target for GPU acceleration. In a traditional sense, these cloud resolving model simulations are typically about 100 times more expensive than the traditional E3SM model would be. And this is replacing the deep convective parameterizations in the model. So when we port this to GPUs, we get significant speed up and are actually able to run this model at somewhere near the target of 5 simulated years per day. Previously, we had run this with OpenACC directives, but since then, Again, we can talk offline about the reason for this choice, but we found it more stable to move over to portable C++ libraries, namely Cocos, and a library that we have in-house called Yet Another Kernel Launcher. So many of you are already familiar with Cocos. It's a very stable product used by many codes. So I'll just take a brief time to describe what this YACL portability library is. It's relatively small. It's about 5,000 lines of code in the core of it, and there's about 2,000 or 3,000 lines extra code in the extensions. Something unique about YACL is that it allows Fortran-like behavior in the resulting C++ code. So we can create user-level code where we have multidimensional arrays that carry the metadata with them, just like Fortran. You can index with the leftmost index varying the fastest, i.e. column major ordering. You can also have arbitrary lower bounds that default to 1 instead of 0. And we have a growing library of Fortran intrinsic functions like sum and maxval, maxlog, things like that. So when you actually port the code from Fortran to C++, which we have a fair amount of code we had to do that for, the loop structures look a little different because we've had to express them a different way that is very Cocos-like. But the resulting code inside those loop bounds looks almost identical to the original Fortran code. In most of the cases, it looks exactly the same. So it enabled us to do some pretty fast porting. We also have an efficient pool allocator that's automatically enabled for all allocations and array creations in YACL. And this helps us because it's very common, well, in a lot of codes, period, but especially Fortran codes, to do frequent allocations and deallocations. These have significant penalties on hardware backends like CUDA and HIP, assuming SYCL is probably in the same boat. So this allows us to run our workloads with allocations wherever we want them with almost no penalty. Again, we have very small workloads, so these latencies are extremely important to handle in our application. We place a heavy emphasis on simple readable syntax with minimal developer concerns, and just enabling a code that looks like domain scientists are used to looking at. It currently runs on CPUs. We have a CPU threading backend with OpenMP. We have NVIDIA GPUs covered by CUDA, AMD GPUs covered by HIP, and Intel GPUs covered with SYCL. And that effort was handled by Isaac Lingas and even more so by Abhishek, who will talk on the next slide, where we find that SYCL itself can target all of these hardware backends. So technically, we have multiple avenues to all of the GPUs using YACL. So I'm going to hand this over to you, Abhishek, to speak to this last slide.
Thank you. So this slide mostly covers about YACL, which is a portability layer for E3S and MMF project. And YACL uses SYCL as one of the backends. The initial idea was SYCL would be used for Intel GPUs. And very recently, SYCL implementation from the compilers has matured enough that it can itself be a portability layer. So we tried using SYCL backend of YACL to run on all three hardware architectures, namely NVIDIA, AMD, and Intel. On the extreme right, we have used Intel LLVM as an open source compiler to work to check what aspects of YACL are really working on non-Intel hardware, so to speak. So the extreme right, you just see the DPC++ is a compiler built on like LLVM ecosystem, and it just to AMD and NVIDIA, it piggybacks on ROCm and PTX plugins, so to get it working on non-Intel hardware. So this table briefly shows the features of SYCL that is explicitly being used in YACL and tested on non-Intel hardware. There are quite a few caveats, and I just point out here that, yeah, there is a need to specify subgroup size, which is nothing but warps on NVIDIA architectures and wavefronts on AMD architectures. So these are the minor details that one needs to tweak for any non-Intel hardware. And again, all these tests were conducted at JLSE at Argonne, and all, the compilers were specifically built with CUDA and ROCm versions as shown in the graph. So this is nothing but like a brief test whether the features that we use in SYCL backend of YACL can work on non-Intel hardwares in a portable way. That's all.
Yeah, thanks very much. With that, we'll go ahead and take any questions if anybody has any.
Hey, Matt, Zach.
I'm sorry, I'm having trouble hearing the question.
Hey, can you hear me? This is Zach. I messaged you in the chat.
Oh, sorry, I don't have access to the chat right now.
Okay, I just wanted to ask about the mixed precision stuff on Summit. Is this working already with your project? So I know Summit has like the mixed precision capabilities. I mean, I think that's what the idea was. Is that implemented yet with this problem?
That's kind of orthogonal to this
Okay.
software. We're not using mixed precision currently in the multi-scale modeling framework code, but there are options where we could potentially use single precision for certain parts of the code. That's something we're definitely interested in, but not actively working on quite yet.
Perfect, because we just have a bunch of stuff ready to go then for you. So let's talk after. Thank you.
Yeah, great.
All right, well, thanks. Thank you, Matt. Thank you, Abhishek. And we have a few minutes left. Were there any questions for any of our presenters? All right, well, if not, I want to thank our presenters, both from the L4s from the facilities and from the folks from the projects for presenting. I thought those were all very interesting talks today. And I want to open the floor more generally. We have a number of people here from the facilities. So if there's anybody from an AD or SD project that has sort of a more general question, this might be a good place to ask it. Were there any sort of more general questions for anyone at the facilities or in AppInt?
Yeah, I'll ask questions if I can.
Sure,
Hey,
go
man.
ahead.
Hey, Zach. Sorry, Matt just told me about this earlier today, and I didn't realize. And I was talking to him about doing some things. Anyway, I'm Zach, by the way. I was the householder fellow at Oak Ridge, and I just left, and I'm working remotely. But we're doing I'm working on a bunch of things with mixed precision calculations and how to implement it with machine learning and all this stuff with any time dependent problem. We just working on with Andrew Kreislieb and Sibel Gottlieb. And I was just trying to see if that was something you guys were interested in with your projects, because I have a team of about like 15 people, like we're all working together, and we were just trying to find an interesting problem. And I think you guys have like 20 of them. So I just want to say hi, and I guess I'll just email Matt. I'll go through Matt, and then if I can he'll introduce me to everyone, and then we can figure out, play matchmaker and see who can help each other. All right.
Yeah, that sounds good. Yeah, it probably isn't enough time to get you together with people in real time here, but
I just wanted to more say hi and put a name to the face on you guys. Thank you.
All right, thank you. Were there any other questions or comments? If not, I did want to, I had one thing from my end. I mean, if you look at a lot of the AppInt work and a lot of talks, you hear a lot of discussion about, porting codes to different programming models, and in many cases, codes supporting multiple programming models. And so I think one of the things, from the facility side, we're concerned about is, the programming model space, and does it address the needs of the application folks? There are some, like CUDA, that are really sort of vendor specific, though there's, of course, the HIP variant, I guess, if you will, of CUDA, that runs on AMD, and there's some preliminary efforts to get that to work on Intel GPUs. In addition, there's some portability, some level of portability developing in SYCL. And of course, things like OpenMP are supported by all the vendors to varying degrees. So there's some portability potential there. And then there's more general, sort of specifically portable frameworks like Cocos and Raja. And there is actually a session at the community BOF days next week, next Wednesday in the morning, that's going to be talking about portability and performance portability specifically. But so if anybody's interested in, I think the folks from the facilities, it would really benefit us to hear people's views about, their preferred programming models and what they would like to, what their plans are for portability for their applications, if they plan to run across multiple facilities, because this is a challenge, and it's something that we've had to spend a fair amount of app in time, I think, helping people, adapt to different programming models, and then also make sure that those programming models, while Cocos is portable, it's a non-trivial amount of effort to get Cocos to run on a new architecture. So there's a lot of investment there, that we probably need to understand how that fits into the bigger picture. What the applications want to do going forward, especially as we look forward to the next generation of architectures, which may present even more problems potentially. Anyways, just a thought. I know we're out of time at this point, and I do want to thank all our speakers today and everyone for attending, and thank you all, and enjoy the rest of the ECP annual meeting.